Nickel catalyst applied to styrofoam reaction. Potassium effect on the inhibition of methane formation. This work was written by Alan Taskin, Adriano Braga, Adriana Palhares, Alejandro Lopes Castilho, and José Maria. Steam reforming is a promising method to produce hydrogen, a clean fuel that presents as burning products only water and energy. The most used method to catalyze this reaction is nickel, a transition metal that has low price and high activity. However, due to its high activity, nickel catalysts lead to methane formation. Once the intermediates formed during the reaction are deposited at catalyst surface and then hydrogenated. Changing those catalysts with promoters as potassium has been described to avoid methane formation, although their effect on hydrogenation of intermediates CHX was not described before. The use of compounds that will form different CHX species during its decomposition will help to understand the role of potassium in avoiding methane formation. The goal of this work is to evaluate the potassium promoting effect on nickel, support manganese aluminate catalysis at methane formation during styrofoam reactions of organic molecules through the hydrogenation inhibition of CHX intermediates and consequent its oxidation. The support was synthesized following the Sol-Gel methodology previously described by Avila Neto 2012. The wet impregnation was carried out with nickel nitrate as precursor in ethanol, and the same method was used to impregnate potassium using nitrate as precursor in water solution. The final samples were labeled with the total nickel weight, 8%, and amount of potassium vary from 0.5 to 5% in weight. The materials were characterized by BET surface area, X-ray diffraction, and Xanis in situ during reduction step, TPR with hydrogen, transmission with electron microscopy, XPS, and infrared. The catalysts were used at phenol styrofoam and ethanol styrofoam to analyze the effect of potassium at CH and CH3 species, and later the sample will be tested at butanol styrofoam to elucidate the hydrogenation of CH2 intermediates. The theoretical calculations were performed by Professor Alejandro to analyze the system stability. The prepared catalysts were applied to phenol styrofoam to verify the CH species under hydrogenation. Once under normal conditions there are no methane formation. The catalyst 8 nickel presented high selectivity to methane above 60%, although the promotion with 0.5% of potassium already decreased to less than 40% the selectivity to methane. The sample with 5% of potassium reduced the selectivity to less than 10%. It shows that potassium effect to avoid CH hydrogenation, allowing the oxidation to form CO and CO2 by water gas shift reaction. The ethanol styrofoam was used to check the effect of potassium in CH intermediates. Without hydrogen, only can be observed decrease of nickel temperature activation, as described by Xanis data. Then, with hydrogen feed, the potassium presence allowed the styrofoam at low temperature, promoting oxidation. But at high temperature, the potassium effect at methane inhibition is modest. The theoretical calculations were done by Professor Alejandro to check the system carbon hydrogen nickel potassium stability. It was concluded that for CH system, more potassium offers high protection to CH group once it presents high energy. For CH2 system, the potassium seems to offer protection to CH2 group but less than to CH. And for CH3 system, potassium does not present protection to hydrogenation. Conclusions: the effect of potassium suppression of methane formation is strongly dependent on structured organic compounds. For intermediates as CH and CH2, potassium is efficient on suppressing hydrogenation to methane, when an aromatic is used, as phenol, whereas in linear compounds such as ethanol, the effect of potassium is modest. Some tests with butanol still will be performed to check the effect of blocking CH2 intermediates hydrogenation. System nickel potassium decreases the energy to CH oxidation, which favors the CO formation. The DFT calculations indicate that potassium interacts with nickel surface in the way that increases the rate of adsorption of CH and CH2, which avoids the full hydrogenation towards methane.